Hey guys.
Hey, Professor. How are you?
Good. How are you? How was your long weekend?
It was pretty long. Could have been longer.
Of course, always could be.
Oh, Professor, have you been during summer? Was there any notable games you played?
Um, I did start playing this game on phone called Wild Rift, and so it's basically the mobile version of League of Legends.
Oh, okay. Yeah, I think I heard of it.
hmm
All right.
So me and my friends we played League of Legends back when we were in college, but it kind of got a little bit too intense for us, and so um we started playing that instead, and it's a lot more chill, and so we like it a lot better.
What do you mean by chill?
It's people don't yell at you as much.
Ah, okay, okay. Yeah,
but
that's what
but
you meant.
even then, like, you can turn off the chat, and so you don't have to read any toxic chat.
Ah,
So
okay, okay.
also the games are a lot shorter, and so it's
Oh, yeah,
the games are only
definitely.
about 20 minutes max, whereas like in PC League, like the games could be like 15 minutes to an hour, and then
Yeah, that's right.
like when you lose those, it just feels really bad. So with 20 minutes, it's a lot less it's a lot less stressful.
Yeah. I remember one time I was playing a bot game and someone got pissed at me just for being in his lane on accident.
Oh.
And I was like, dude, this is a bot game.
Yeah, people take it pretty
Yeah, yeah.
seriously.
That's why I stopped playing. Yeah,
Yeah.
it's kind of crazy. Professor,
Yep. So,
I have a quick question about fluids,
yep.
if that's okay.
Sure.
Back with Navier-Stokes, why was it that the equation worked with assumptions, but we couldn't use it without, like, why couldn't we use it without any assumptions?
It's the equation itself is just too complicated. I mean, it's the like you're taught you have a partial differential equation, and normally, normally because you're solving for velocity components, right?
Right.
And so there's technically three components out there. So there's the x component, the y component, and the z, and you also have pressure too. And so there's 4 different things you have to solve for, and then you have 4 different independent variables that you are accounting for too: x direction, y direction, z direction, and time. And so you have kind of way too many equations, kind of way too many unknowns, and it's in differential equation form. So I think right now it's literally impossible to solve those equations without any kinds of assumptions. So yeah, and actually it's one of those problems where I don't know who's offering it, but if you can actually come up with like a solution to Navier-Stokes without any assumptions, it's literally one of those $1 million questions where you'll earn $1 million for it. But yeah, the short answer is that it's just that it's too complicated without the assumptions.
All right, thank you.
Yep. Hey, Jesus, how's it going? Good. Did you have a good weekend? Nice. All right, it's 1 o'clock, so let's go ahead and get started today. All right, good afternoon, everyone. How's everyone doing today? Did everyone have a good weekend? Good, good. I see some thumbs up. Yeah, always nice to have a 3-day weekend, but it's never long enough. So this weekend I went to Joshua Tree with my fiance. So it was the first time I went, and so it was really nice. It was really hot, but it was really cool seeing all the rock formations and the trees and the cacti and everything over there. And we went stargazing at night too, so it was beautiful because it was if you've ever been out there, it's they do a very good job of keeping the street it's really down low. And we went on a night when there's no moon too, so we got to see really nice a really nice night sky. Yeah. How many trees were there named Joshua? I don't know. It was too many to count. Yeah, amazing views, amazing. Yeah, we saw the sunset up at Keys Point, which is like kind of on the southern tip of Joshua Tree, and it kind of overlooks this valley, and it was beautiful, top notch. Definitely recommend it if you ever get the chance. Okay, so today we're going to be starting something new, and so today we're going to be starting lecture notes 02 on present worth analysis. But actually before that, I do want to make sure that we go over the compound interest tables again, because I know I kind of rushed that at the end of last week, and it's something good to know for this class because it'll save you a lot of work. All right, so that's the plan for today. One announcement I want to make is that remember homework 1 is due tonight, I believe, right? And so it's due tonight at midnight. So make sure you get that, you submit that to Canvas, before the deadline. Okay. And I just posted homework 2 today as well. All right. And so you won't be able to do much yet, but I think probably after Thursday's class, you should be able to do everything on that homework. Okay. And that's going to be due a week from Thursday. So that's going to be September 16th. Okay. So a little bit of a quick turnaround, but there's kind of a lot of content that we're going over kind of early on in this class. And I want to make sure that you guys are getting the practice in with it, while it's still kind of fresh in your head. Okay. All right. Any questions on anything before we get started for today? Okay. All right. And so let's go over just quickly again on how to use the compound interest tables, because I know I kind of did that a little bit in the rush next week. Okay. All right. And so the whole idea with compound interest tables is to kind of simplify a lot of the calculations that we were doing, for most of last week. Okay. And so in this class, what you're going to be doing a lot is you're going to be converting cash flows from one form to another. Okay. And just to remind you, we have four different types of cash flows that we went over last week. Okay. And so one, we have a present sum. Okay. And a present sum of money represents a single lump sum of money that you have, today, right now, right? And so the symbol we gave for that is P. Okay, we also had future sums. And so future sums are a single lump sum of money that you're going to have sometime in the future. Okay. And remember, we can't equate, the value of money is different in the present and the future because of interest rates, right? And so that's the whole reason we have to do conversions. Okay. We also have the uniform series. And so the uniform series represents kind of a regular recurring payment that occurs over a period of time. Okay. And so that's used to represent things like maintenance costs, used to represent things like salary, okay, or maybe revenue. And so any payment that you either receive or you pay out that occurs at a regular interval, and it's the same amount every single time period. Okay, and we also have arithmetic gradients. And so that was kind of the very last one we went over last Thursday. And so arithmetic gradients represent something that's, a payment that's increasing over time, right? And so that's could be like an increasing maintenance costs or, other things like that, okay? And so we have P, F, A, and G. And what we learned last week was all the different formulas that we can use to convert between them, right? But those formulas are not the easiest things to use, and so even though they're not hard, but they're just kind of annoying because these equations are kind of big, they're kind of cumbersome, they're not and it's kind of really easy to kind of make like a mistake punching into your calculator or something like that, okay. And so and with the amount of cash conversions that we're going to be doing in this class, it'd be really convenient to have another way to perform these conversions that is less prone to errors. Yeah. Yes. Oh, sorry. A couple questions. Yes, arithmetic gradients can be money decreasing over time. Yes, then you just have a negative. Yeah. And Danny, your questions: does lump sum refer to a specific variable like F or A? When I say lump sum, I just mean kind of the money only occurs at a single time point, right? And so if you compare that to like arithmetic gradient or uniform series, those are payments that are spread out, each occurring at a regular interval. And so when I say a present sum and a future sum is one lump sum, that means it just occurs at one time point. Yeah, single error. Okay. And so, that's where the compound interest tables come in, because it's a really nice way to perform these conversions without having to use a formula. Okay. And I know a couple of you guys have used this for the homeworks already, which is great, and so if you've already kind of used this for homework 1, then that's good, because it's it's something good to get used to. But let's go over kind of the process again, just so kind of we're all on the same page. Okay. And so in order to perform a conversion, you kind of need, I would say 4 pieces of information. Okay. Okay. And so the first thing you need to know is the form of cash that you're converting from. Okay. Next, you need to know what the interest rate is. Okay. Next, you need to know the number of time periods. Okay. And then lastly, you need to know what you're converting to. Okay. And if you have all these pieces of information, then you can use the compound interest tables. Okay. Okay. And so I think kind of the easiest way to kind of show this is with an example. And so before I jump into that, are there any questions on this? Okay. Okay. So let's redo one of the examples we did kind of at the end of Thursday, but let's do this now with the compound interest tables. Okay. Okay. I'm not going to write the flavor text for the problem again, but basically for this problem, we have a uniform series and an arithmetic gradient that we want to convert to a present worth. Okay, we want to convert both of them. if I recall correctly, I think, this problem is your friend just bought a car and he wants to set aside money now to cover all the maintenance costs. Okay. And so these maintenance costs have a base value. It's going to start at $120 a year. Okay. And then every year after that, it's going to increase by $30. And so we represent that with an arithmetic gradient of 30. Okay. And so for this problem, we want to convert both of these amounts to a P, or a present sum, and then add them together. Okay. Okay. And so, with this, we need to perform two conversions. And so we're going to look up two things in the table. Okay. All right. So let's start analyzing this problem. And so we know that we're starting with an A and we're starting with a G. Okay. And so that's already our first piece of information. And so we already know what we're converting from. Okay. Okay. Right. And we also know what we're converting to, because we're converting both of these to a present sum. Okay. Okay. All right. And so we have two conversion values that we need to look up to, right? And so we need to look for one conversion value that goes from A to P, and another conversion value that goes from G to P. Okay. And so let me go ahead and separate those two out. Okay. Okay. And so the way that the compound interest table kind of represents this is that you do what you're converting to over what you're converting from. Okay, so you kind of make this kind of like pseudo fraction thing. Okay, and so for converting from A to P, the way that we can represent this is we can do P over A. Okay. Okay. And then to convert from G to P, we call that factor P over G. Okay. Right. And so as you can see in both cases, we have the quantity or the form that we're converting to up top, and then the form that we're converting from on the bottom. Okay. All right. And so there's that. Okay. Oh, I forgot to give you the interest rate and the time period. Okay. And so for this problem, let's say we have a 5% interest rate. Okay. And then we're going to be doing this over 5 years in a row. Okay. And so our I is going to be 5% and our N is going to be 5. Okay. Okay. All right. And so now let's kind of write down the form that we need in order to use the compound interest tables. Okay. All right. And so the way we're going to do this is we're going to say that P, which is the total present sum of what we have in the present day, okay, this is going to be equal to our A, where our A in this case is 120, but let me just keep it in symbols for now, okay. 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 Next, we're going to multiply this by our P over A factor, okay. And this is going to be at an interest rate of 5% for an N of 5 years. Okay. Okay. So I'm putting all this in parentheses right now, just to kind of group them all together. Okay. To this, we're going to add our G conversion. Okay. So it's going to be plus G times the P over G factor for an interest rate of 5% and an N of 5 years, okay? Where once again, the last two numbers here are the interest rate and the number of periods, okay? Okay. And so this is the form that you'll see me write these in usually, okay? And so whenever I need to perform a conversion, I usually make this parentheses, which has these 3 entries inside, okay? And so the first entry in the parentheses, this is always going to be which conversion factor that you need, okay? And so that's going to be some fraction of something, right? So P over A, okay? It's just a symbolic fraction, and so you'll kind of see what you'll kind of see what I mean when I show you the tables. Next, we'll have the interest rate, and then we'll have the number of periods after that, okay? All right, so in the problem, we're given these already. And so in the problem, we know A is 120. Okay, and we know G here is 30, okay? Okay, right, and so we know what to plug in for A and G. And then what we need to do next is we need to look up these values here look up these conversion factors here in the table, okay? And I'll show you how to do that in a second. But but I'm going to switch to my computer monitor for that. So before I do that, are there kind of any questions on how we kind of set up this conversion here? Okay. All right. So let me go ahead and share my laptop screen so I can show you how to look up these values here. Okay. All right. So I'm going to share screen 1. Okay. All right, and so what you're seeing here is the compound interest tables PDF, and so I've uploaded this onto Canvas. And actually, you know, if you want to see where it is on Canvas, if you go to our course homepage, okay, and you'll see that I've made this new thing on the course homepage called compound interest tables, and so you can just download that PDF there. Okay. All right. Okay, and so once you download that PDF and then you open it up on your computer, then you'll be seeing this. Okay, and the way to use this is that you can see it's a 32-page document. Okay, and you can see that there are a ton of numbers, right? And so it's a little bit easy to kind of get lost under what's going on. Okay, but you know the way you use this is that you first look up the compound interest table for the interest rate that you're looking at. Okay. And so for the problem that we were just doing, we have an interest rate of 5%. And so I'm going to scroll all the way down until I reach the interest table for 5%. Okay. Okay. And so now I'm here. And so you can see here that, you know, we're at the compound interest table for 5%, which is what we want. Okay. Right. The next thing that's useful to do is you can either start by looking for the column that you want or the row that you want. Okay. And so you can see here that the compound interest tables are sorted by the columns for the different conversion factors, okay? Right? And so first, let's look for the column for converting from an A to a P, okay? And so remember that that symbol that we gave it was P over A. And so we can see that, you know, we want this column here, right? We also want the column for P over G. And so P over G is going to be this column right here, okay? Next, you're going to look at what row that you want, okay? And the rows are given by the values of n for the number of time periods, okay? And for our problem, we have a time period of 5, okay? And so we're going to follow this all the way over to the right until we get the factors that we want, okay? Okay. And so you can see for our problem, our two conversion factors are going to be 4.329 for our P over A factor, and then 8.237 for our P over T factor. Okay. And so now all we have to do is we just have to take these conversion factors, plug it back into our formula, and then just perform the arithmetic, and then that's going to give us our total solution. Okay. Okay, any questions on that before I swap back to my my iPad screen?
Professor?
Yep.
Would there be a time where the interest isn't on the table, then we would have to do it manually?
Yes, no, it's a great question. So if you'll notice from the table, oops, I kind of scrolled. And so the table only gives you interest rates in kind of batches of, you know, of usually nice whole numbers, but you know, they have some decimals that are closer when you're closer to 0. But if you're given an interest rate that doesn't have a table for it, I would recommend that you just use the formulas for it. I think that gives you the cleanest answer. Someone in the chat suggested interpolation. You can do that too. if you really want, but I think that actually ends up being a little bit more work, because you kind of have to swap in between two tables and then kind of interpolating in between the factors. And so I would recommend that you use the formulas. You'll get a much more exact answer that way, because with interpolation you kind of assume kind of a linear trend in between the two interest rates, which is not always the case. Okay. And so if I give you an interest rate that's not in the tables, then I would use the formulas. But if the interest rate I'm giving you is pretty close, and so let's say I give you 4.9, that's pretty much 5, and so the difference between 4.9 and 5 is not that intense, and so you can probably use the interest. You can probably just round up and use the interest tables for 5. Yep. All right. Question. So is there such a MATLAB code that does this for us? X compound interest. You could actually do this in Excel. Actually, it could, because these are very much economic calculations, and so accountants and stuff, they use Excel all the time. And so there's a way that you can do this in Excel. I'm pretty sure there's probably a way to do it in MATLAB too, but I just haven't seen it before. But I know for sure that there are Excel methods to do this, because my friend that's an accountant uses it all the time. Yeah. All right. Any other questions on this before we jump back to the iPad? Okay, so let me jump out of here. Come back here. Do you guys remember what numbers they were? It's okay. I have it written down in my notes. So. All right. Oops. No iPad. All right. And so from the compound interest tables, we were able to look up these values here. Okay. Okay. All right. And so in case you forgot these numbers here, this one, the P over A factor is 4.329. Okay. And then the P over G factor was 8.237. Okay. Right. And so all we have now is just a very simple arithmetic operation. Okay. And so what we have is P is equal to 120 times 4.329 plus 30 times 8.237. Okay. You add these guys together, and what you get is $767. Okay. Which, if you look back in your notes from last week, this is the same answer to that problem that we got before. But before, we used formulas, but here we use the compound interest tables, which was a lot easier. Okay. And so, I know that kind of took a little bit of time, but it was mostly just because I was going a little bit slow. But once you're doing these problems, kind of, and you're kind of using the tables regularly, this is usually a much faster way to go. Okay, and for problems where you have to do a lot of conversions, which we're going to do very soon in the next unit, okay, then the compound interest tables will save you a lot of work. Okay. All right, any questions on this example before we move on to present worth analysis? Okay. All right, and so that's kind of that kind of marks the end of our first big lecture note series, which is on kind of the time value of money and cash conversions. And so now our next few units are is all going to be about how do we actually use this to do something useful. Okay, and the first type of analysis that we'll learn is called present worth analysis. All right. And so, in the previous unit, we learned all about the different kinds of cash flows, the formulas, and the way to convert between them. Okay. And so, that's kind of nice, but, the question now is, how do people actually use this in engineering economic analysis? Okay. And so kind of the first real way that this is used is to perform comparisons between economic alternatives. Okay. Okay. Because one situation you'll find yourself in a lot, once once you get out into the workplace, is that you're gonna have to make some decisions about what parts to buy, what resources to purchase, what kind of business strategy that you want to have with your product. Okay, and you're going to be choosing between a lot of different alternatives. Okay, and it's a lot of times it's not as simple as just simply saying that this one is going to make you $500 and this one's going to make you $400, right? It's usually not going to be that simple. And so each one's going to have kind of a really complicated cash flow structure, going to have a very different maintenance cost schedule, all these different things. Okay, and so for these situations where you have these kind of complex cash flows, you kind of need a way to say definitively and systematically that one is better than the other. Okay, and that's exactly what present worth analysis is going to do for us. Okay. Okay, and so before we actually start doing some of these problems, it's good to lay out some assumptions. Okay. And so we're treating this almost exactly like a like a typical engineering problem, right? So you almost always start with your assumptions, okay, and then you kind of use those assumptions to kind of help simplify your problem, okay. And so economic analysis is no different. Okay, there's always going to be assumptions. It's just whether it's just kind of being aware of what these assumptions are, just so that you kind of know what you're doing. All right, and so the first assumption is something that we've kind of already talked about with cash flow diagrams, and that's the end of period assumption. Okay. And so the end of period assumption basically assumes that all cash flows in a given period are assumed to happen at the end. Okay. Okay. And this is just mostly just for simplifying our cash flow diagrams and for simplifying our conversions as well. Okay. And so even if you know that you're paying the maintenance guy on the 15th of the month, we're going to assume that that doesn't happen until the very end. Okay. And that's just to make sure that all the cash flows in a given period, that they all stack on top of each other. We can perform our conversions with whole numbers. Okay. This is kind of just a really necessary assumption just to kind of simplify our whole process. Okay. Okay. All right, next. Okay. Next is our assumption on inflation or deflation. Okay. And so we'll talk about inflation, later on in the semester. I think kind of right before, it's going to be one of the last things that we do. Okay. And so if you're curious, inflation kind of refers to the fact that, generally over time, the price of goods tend to go up. Okay. And so, people always kind of joke that, a carton of milk doesn't cost what it used to a long time ago. And that's because of inflation, right? And so naturally, because of inflation, the cost of goods is going to go up over time. Okay. And so the question of inflation kind of becomes relevant for these kinds of problems, because a lot of times we're looking at economic analysis with a project horizon of many years. Okay. And so naturally you would think that over a 12-year period, the cost of steel or the cost of wood or whatever your resource is going to go up over time. Right. And so it's a real thing. But for now, we're just going to ignore these effects. Okay, just for the sake of simplicity. Okay. And so inflation, it does make a big difference, but when you're kind of first starting out, it's always good to kind of make this as simple as possible, right? And so if you think of in physics, right, you a lot of times you're going to ignore friction, you're going to ignore air resistance, and so this is kind of the same thing, right? So even in reality, friction and air resistance, they make a big they make a big impact. But when you're first learning projectile motion, it's best to just ignore that. Okay. Okay. And we're going to do the same thing with taxes. Okay. And so, taxes, obviously are going to have a big impact on our economic analysis, but for now, we're just going to ignore them. Okay. But we'll definitely revisit taxes later on in the semester as well. Okay. All right, and so the last assumption that I want to go over is the mutually exclusive assumption. Okay. Okay. And so what you'll see in these problems that we're going to do is that we're going to be choosing between one option and another one, right? Sometimes even more than one. And so what the mutually exclusive option means is that you can't choose all of the options. You can only choose one or the other. Okay. And so selecting one option will prevent us from choosing the other ones. Okay. Okay. And so you can only have one. You can't have all the candy in the candy store. Okay. All right. Any questions on this? Okay. All right. And so what are we looking for present worth analysis? Okay. In other words, let's discuss our economic criteria. Okay. Right. And so when we're choosing between economic options, okay, and assuming that everything else is the same between the options in terms of performance, and let's assume that they all satisfy our standards. Okay. The goal in present worth analysis is that we want to choose the option that's the most economically efficient. Okay. 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 And so for present worth analysis, what this means is that we want to choose the option that minimizes the costs, okay, and or maximizes the benefits. Okay. Okay. And so the way we perform this analysis is that, given an economic alternative with all of its associated costs and benefits, what we want to do is we want to convert all of the cash flows for an alternative to a present sum. Okay. Okay. Okay, and so we're going to do this for each alternative. Okay. And so, for the example problems that we'll see later, let's say that you have option A. Okay, so for option A, you're going to convert the present worth, and so you're going to convert all the cash flows to a present sum. Okay, then you're going to compare, the present sum for option A versus the present sum for option B. Okay, and whichever one is higher, that's going to be the most economically efficient option. Okay. Right, and so there's really nothing new compared to what we've done previously, right? In fact, we're using all the same skills that we've done before, and so we're going to be drawing cash flow diagrams. We're going to be doing cash conversions. Okay, the only added step here is that we're just going to be comparing two numbers against each other, right? And then all you have to do is just to choose which one is higher than the other one. Okay. Okay, and so the application of this is actually pretty straightforward. I think it's just kind of getting all the stuff that we've covered up to this point, getting good at all those things. And then once you're good at all those things, then present worth analysis is kind of a very, very simple, straightforward application. Okay. All right. Any questions on this before we jump into an example? Just to kind of show you what I mean. Okay, so let's do an example just to kind of show you this this in action. Question, could I go back one page? Yes, I can. Okay, are you good, Kyle? Okay. All right, so let's do an example here to show this in action, right? And so let's say that you work for an engineering firm, and this firm is deciding between the purchase of two different machines. Okay. Okay. And these machines are designed to save some costs for the company. Okay. All right. So let's say that both machines have a useful life of 5 years. Okay, and so the n is going to be 5. Okay. All right, and so let's go over the options. Okay. All right, so let's talk about machine A first. Okay, and so machine A is going to cost the company $10,000 to buy. Okay. Right, so that's its initial cost. And then by purchasing this machine, the company expects that it's going to save $3,000 per year. Okay. Okay. All right, and so you'll see this wording used sometimes in these problems. And so when a problem tells you it's going to save X amount of money each year, okay, the way that you can kind of represent that in a cash flow diagram or as a cash flow, you can represent this as a benefit. Okay. Because as one of our great founding fathers used to say, a penny saved is a penny earned, right? And so if you're saving $3,000 per year, that means you have $3,000 more per year than you did, before. And so you can just kind of model that as a benefit. Okay. right? So even though it's not explicitly saying that the company is making $3,000 a year in revenue, right? And so but saving $3,000 is kind of the exact same thing as you know, as getting revenue. Okay. All right, so machine B. So machine B costs a little bit more. And so machine B is going to cost us $13,500. Right. And then the savings for machine B will be $3,000 in the first year. Okay, so in year one. Okay, but this is also going to increase per year by $500. Oops. Okay, and so machine B has a little bit of a gradient option going on. Okay, right, and so machine B, you know, in year one is going to be a benefit of $3,000, but each year after that it's going to increase by 500. So it's going to be 3,500 in year two, 4,000 in year three, and so on and so forth. Okay, all right, and so if we assume that the interest rate, let's say that the interest rate in this case is 7%. Okay. You know, let's use present worth analysis to determine, you know, which one of these machines is more economically efficient. Okay, right, because just by looking at this, you know, it's not immediately clear, right? And so machine A is cheaper, but you know, machine B, you know, the savings are going to ramp up per year. Okay, and so the question is, you know, is that kind of ramp up in savings, is it worth the extra $3,500 that we're going to pay up front, or is it or is it not? And it's better to go with machine A. Okay. Okay. Any questions on this before we work on these solutions? Okay. All right. And so for this problem, we want to use present worth analysis. To determine which option is better, economically better. Okay. And so let's start with drawing the cash flow diagrams. Okay. It's always a good idea to start with the cash flow diagrams, especially when you're just starting out with these. Okay, just so that you can visualize, you know, what's going on. Okay, so for some problems, I'll explicitly say you have to draw the cash flow diagram. But even for problems where I don't ask it, you know, it's a lot of times it's a good idea to draw the cash flow diagrams, because otherwise it can get really easy to kind of, you know, mess things up, especially for the more complicated ones with like gradients and things like that. Okay. All right, so let's draw the cash flow diagram for machine A first, okay? Okay, and so we have 5 years here. Okay, so 0, 1, 2, 3, 4, 5. Okay, and so machine A, we know that it has an initial cost of $10,000, and so let's draw one down arrow here. It's going to be $10,000. Okay. And then the savings each year is going to be $3,000. Okay. Okay. Right, and so for machine A, you know, from the cash flow diagram here, we see that we have a simple kind of initial cost, and so that's already in P, and so we don't need to convert that. And then we have a uniform series here of $3,000. Okay. Right, so now let's do B. And so for option B, we're going to do 0, 1, 2, 3, 4, 5. Okay. Okay. So we know for option B, the initial cost is 13,500. Okay. Okay. And then for the savings each year, we know that they're going to start at 3,000. And then each year after that, it's going to increase by 500. Okay. Okay, all the way up to 5,000. Okay. All right. And so we can see for option B here that we have some arithmetic gradient going on because it's, it's going upwards. All right, and so from these cash flow diagrams, we can go ahead and write down, the cash flows that we see. Okay. Okay. And so for machine A, we can see that we have an initial cost of $10,000. And so we can represent that with the P of negative 10,000. Okay. And then we also have a uniform series of worth $3,000. Okay. Okay. And then for option B, what we have here is that, we have initial cost, just like option A. We have our uniform series amount, which is 3,000. And we also have an arithmetic gradient of 500 because that's how much it's increasing. Okay. Right. And so to perform present worth analysis, we have to kind of convert everything here into a present sum. All right, so let's start with A first. All right. I call this PA total, or call this PWA. How about that? PW for present worth. Okay. And the A is indicating that it's option A. Okay. All right, and so to compute the present worth of A, we're going to start with PA. Okay. And so since PA is already in a in a present form, we don't have to do any conversion on this. Okay. Okay. Because if the cash flow that's given to you in the problem is already in the form that you want, then you can just plug it right in. You don't have to convert it. Okay. Okay. Next, we have the uniform series amount from the savings. Okay. Okay, and so that's going to be AA. Okay. And then here we need to perform a conversion. And so let's use the same kind of format that we used kind of earlier in the class today. Okay. And so we know that we want to convert to a P from an A. And so the factor for that is going to be P over A. Okay. The interest rate in this case is 7%. Okay. And then the N for this guy is 5 years. Okay. Right, and so I'm going to do this problem with the compound interest tables. Okay. And so if you look up in the tables, because I actually don't have this written down right now. Okay. If you look up at the tables for 7% with the P over A factor for an N is equal to 5 years. Okay. Then what you get is this factor right here is 4.1. Okay. 4.100 if you want to be more precise. Okay. Right, and so if we plug everything in here, we have a minus 10,000 plus 3,000 times 4.1. Okay. And so if we plug all of that in, then what we get is a present worth of $2,300.59. Okay. Right. And so what this analysis is telling us is that if we choose to go with machine A, basically all the savings that we're going to accumulate over the years is going to be the exact same as if someone wrote us a check for $2,300.59, and they just gave it to us today. Okay, and so this is the present day or present worth of option A right here. Okay. All right. Any questions on this and kind of how we obtained that number? Okay. All right. So now let's do the present worth for option B. Okay. Okay. So we're going to do present worth of B. Okay. And so present worth of B is going to be PB, right? So PB is already in present form, and so we don't have to convert this. Okay. Next, we have the uniform series for B. Okay. And this is going to be a conversion from a uniform series to a present sum, and so we need P over A. The interest rate is 7%, and the N is 5. Okay. Right. And then finally, we have to convert the gradient, and so we want a P over G factor, 7% and 5. Okay. We can look these guys up in the table. And so this one we know from the previous part because it's the same conversion factor, right? So P over A for 7% in 5 years. We know that this is going to be 4.100. Okay. And then if we look up this factor, the P over G factor for interest rate is 7% and N is equal to 5. We look this up in the table. This is 7.647. Okay. And so we plug all that in as we have minus 13,500 plus 3,000 times 4.100 plus G, which was 500 times 7.7647. Okay. And so we plug all those in, and what we get is $2,623.92. Okay. Right. And so if we chose option B, then it would be the same thing as if someone handed us a check for $2,623.92 today. Okay. And so if we compare this compared to what we got from machine A, we can see that machine B has a higher present worth. Okay. And so the most economically efficient option for this problem is to choose machine B. Okay. Right. And so that last step there is really important because when you do these problems, I think the temptation is to kind of compute the present worths for all the options and then just kind of stop there. Okay. I want you guys to take that one step further and tell me which one is the highest, right? I know that I can read your work and I can see which one is the highest, but remember the whole point of present worth analysis is to make a decision on which economic option to go with. Okay. And so I want you guys to make those decisions too. Okay. And it's really just as simple as just saying, which one is the highest, and then just tell me which one is the highest. But I want you guys to kind of explicitly write down that machine B has the highest present worth, and so therefore it makes the best choice for this thing. Okay, it's a little bit. I know it's a little bit pedantic, but I don't want you guys to just stop. I don't want you guys to take away from this part of the class saying that all we have to do is just compute the present worths of everything, right? I want you guys to make a decision based on the present worth that you computed. Okay, so take that extra, 2 seconds to say that choose option B or choose option A, or just whichever one is the highest. Okay. All right, question. So there's a question in the chat that says, so this means that B will return the most profits post-purchase. Yes, yes. And so what you can say from this is that, even though B has a higher initial cost, over the 5-year span, it's going to return more. It's going to return more money than, the extra cost that you paid upfront. Yeah. Yeah. And so that extra $3,500 is worth it in this case. All right. Any more questions on this example before we move on? Okay. All right. So let's that was kind of your first taste of present worth analysis. Okay. And so you can see here that it's just an application of everything that we've been doing. Okay. But I do want to go over one important consideration, and that's the time period for the analysis. Okay. And so one really important factor when you're comparing several different options is you need to make sure that their time periods are the same. Okay. Okay. And so in the last example that we did, both machines had a time horizon of 5 years, right? And so we didn't have to worry about that. And so we could kind of perform like an apples to apples comparison. Okay. But if you are doing a problem and the time periods are different, it's not really fair to compare them to each other. Okay. Okay. And the main reason for this is kind of really based on the conversion that we're doing, right? And so, since we're converting everything into a present sum, how many years that the product is active has a really big impact on, on kind of its present worth, right? And so if we look at our previous example and we say that, let's say that machine A will last for 1 more year than machine B, right? And so it has kind of an extra year of $3,000 it can make, right? That's not really fair to compare it to a machine that can only last for 5 years, right? When you're doing present worth analysis, okay? Because you're kind of converting everything back into kind of one lump sum in the present day. Right? If they don't have the same, if they don't have the same project lives, or if they don't have the same, amounts of time that they're active, then that can make, that can really skew your calculations. Okay. But there are going to be cases where you do run into situation with different product lives, and next we'll discuss what you have to do in those situations. Okay. Okay. And so what happens when project lives differ? Okay. Right. And so this is going to happen a lot in reality, right? And so you're comparing 2 different objects, and one is going to last for longer than the other. Okay, that's just kind of a natural thing. Okay, and so you can still do present worth analysis in these cases. You just have to kind of make a small adjustment. Okay. And the adjustment that you have to make is that, you kind of have to force both products or both options or all of the options to have the same time period, okay? And the way that you do that is you find the least common multiple of their useful lives, okay? Okay. And so as an example, let's say that we're comparing two products, and one has a life of 8 years and another has a life of 4 years. Okay. And so let's say that option A has a life of 8 years. Okay. And so let's say we have another option B, and option B has a useful life of 4 years. Okay. Okay. And so these guys have different useful lives, right? And so normally you wouldn't be able to do present worth analysis on this, but if you use the least common multiple, and so the least common multiple between 8 and 4 is 8 years, okay? Then you can do both, okay? And so in this situation, we want to do our analysis with n is equal to 8, okay? Because that's the least common multiple, right? All right. And so that seems, pretty straightforward, right? And so, just choose, whichever, choose a number of years such that both kind of end at the same time, okay? And so for option A, this is great because option A, it was going to last 8 years anyway. And so we just perform that as usual, okay? But now the question is, what do we do for option B, right? And so for option B, we're kind of extending its life by 4 years, right? And so, how do we work on this, right? So how do we extend the maintenance costs? How do we extend the revenue? How do we extend, what do we do if there's a salvage value, right? And so there's, how we handle this is going to be key to this analysis. Okay? And what we're going to assume is that whenever we have to kind of extend the analysis period beyond the useful life of a product, is that we're going to assume that we buy a replacement of this product at the exact same cost when the useful life runs out. Okay. And so for this example here, at the end of 4 years, we know that option B is going to basically, quit or just become defunct at that point. Okay. And so at year 4, what we're going to assume is that we're going to purchase another copy of B at the same price. That's going to take us all the way up until 8 years. Okay. Right. And so this is, and this is a huge assumption here, right? So remember the assumptions that we talked about earlier in the class, right? And so, if you've ever kind of, I think kind of the most tangible example of this is car parts, right? And so if you've ever had something in your car break, 8 or 10 years after you bought it, and you need to replace it, it can be a nightmare to try to find it because it's, because the manufacturer doesn't make the part anymore. And, the ones that do have it have been hoarding it for the last 10 years and are going to charge you an exorbitant amount of money for it. Okay. And so, assuming that a particular machine or particular part is available at the same price years later with no inflation is a huge assumption. I know that, but it's kind of a necessary assumption that we have to make for these kinds of problems. Okay, And so, you'll see, and I think we have time for one more example today. Okay. You'll see that, our next example is going to take place over 12 years, right? And so to assume that something is going to stay the same price over 12 years is pretty huge, but we kind of have to do it for at least for the tools that we have now for economic analysis. Okay. Okay. So any questions on this before we jump into an example? Okay. All right. So let's do an example with some numbers here. Okay. All right. And so in this example, let's say that you work for Southern California Edison. Okay. And so let's say that SCE is considering the purchase of a new pump. Okay. All right. And so we have two options here. And so let's have vendor A. Okay. And so vendor A is offering a pump with a initial cost of $7,000. Okay. The annual maintenance cost for this pump is going to be $1,500. Okay. And then it has a salvage value of $1,200 after 12 years. Okay. And so N for this case, or the useful life, is going to be 12 years. Okay. Right, and so you'll notice here that we have all costs, and so we don't have any benefits, and so that's okay. You can still do present worth analysis in these cases. You just have to find the one that is the least negative. Okay. All right, so then we have vendor B, and so vendor B is going to be selling a pump at an initial cost of $5,000. Okay. And so we can see right away it's $2,000 cheaper than option A. Okay. Okay. Maintenance cost for this pump is going to be $1,000 a year. Okay. And the salvage value is going to be will be $1,000. Okay. Right, but the useful life for this pump is only going to be 6 years. Okay. Right. And so you can see here we have a mismatch. And so option A is going to last for 12 years and option B is only going to last for 6. Okay. And so if we assume an interest rate of 7%, I think, yes. Okay. And so if our interest rate is 7%, let's use present worth analysis to determine which pump is the better option. Okay. Right. And so not only do we have different product lives here, but as you can see here, we're not considering any revenue. Okay. And so when I use present worth analysis on this case, I want to find the one that's the least negative. And so the one that's least negative is going to be the one that minimizes the cost. Okay. All right. And so let's start with the cash flow diagrams, just so that we can kind of see what's going on. And so let's start with option A, because that one's a little bit easier to to C. Okay. Okay, so we have 12 dots. All right. And so in year 0, we purchased the device for $7,000. Okay. Right. And then every year after that, we have maintenance costs of $1,500. Okay. So all these small arrows here are $1,500. Okay. And then we actually do have one benefit here, which is the salvage value, right? So our salvage value represents, what money that we can earn back at the end by selling the parts or whatever. Okay. In this case, we have a salvage value of $1,200. Okay. Right. And so this makes for a pretty easy present worth analysis because we have one present sum or one present amount, which is the initial cost. Then we have a uniform series, which is all the maintenance costs. And then we have a future sum of the salvage value at the end. Okay. And so we just have to convert all of those back to the present day. Okay. And so option A, we've done that before. Okay. And so option B is going to be the one that's interesting because we have to buy a replacement in year 6. Okay. And I'll show you what that looks like in the cash flow diagram, right on the next page. Before I do that, are there any questions on this? Okay, so let me draw the cash flow diagram for option B, and I think that's all we'll have time for, and then we'll wrap it up after that. Okay. All right, so for option B, we have to buy a replacement. In year 6. Okay. All right, so let's draw our cash flow diagram again. Okay, so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. All right, so let's do the first purchase first, right? And so initially, we're going to purchase this machine for $5,000. Okay. And then for the first 6 years, we have maintenance costs of $1,000. Okay. Okay. And then at the end of year 6, we also have our salvage value of $1,000. Right? Yes. Okay. Okay. Just double check that. Yes. Okay. All right, so that's the first purchase, right? And so our first pump is going to last us 6 years. We're going to pay $1,000 per year for the maintenance, and then we're going to sell it for $1,000 at the end. Okay, right? But we have 6 more years to go, right? And so we need to reach all the way to year 12. And so in order to reach there, we need to make another purchase here of $5,000. Actually, let me do this one in a different color just so you can kind of see the difference. And so that second pump, after we buy it, that's going to take us all the way to the end of 12 years. Okay. And so this is all $1,000 here. Okay. And at the end of year 12, we have another $1,000 salvage value. Okay. Right. And so this is how you deal with situations where your product lives are different, right? And so first you find the least common multiple of the of all the different options, okay, of all the years. Then you set that to be kind of the ultimate kind of horizon time, and then for all the options that don't match that horizon time, you just buy replacements whenever one machine retires and it kind of reaches its end. You buy a replacement, and then you just carry on from there. Okay. All right, and so for this one, you can see that our cash flow diagram is a little bit more complicated, and so we have a little bit more conversions to do. But overall, it's not terrible as well. Okay. All right, any final questions on this before we wrap up for today? Okay. All right, and so on Thursday we'll pick up with this example kind of first thing next Thursday, and then we'll finish up our lecture notes on present worth analysis. Okay. All right, so have a great day, everyone. Remember, homework 1 is due tonight at midnight, so make sure you get that in, and I'll see you guys on Thursday.
Thank you, Professor.
Thank you, Professor.
Thanks, guys. Have a great day.
Professor,
Yep.
I have a quick question for the problem where we chose machine B.
Yep.
Did we choose machine B because we did all that conversions to find out which one had more savings?
Yes, and so you don't have to think of it in terms of like savings or anything like that. Just, you're computing a present worth for every option, and you just want to see which one is the highest, and whichever one is the highest, that's going to be the most. Think about it in terms of like economic efficiency, because I think that's a term that kind of covers everything. And so in this case, we actually did have some revenue here, or at least some savings.
Right.
And so choosing option B is going to save us. You can think of it as saving us more money, or it's more economically efficient. Right? But what you'll see, so when we finish up this problem on Thursday, what you'll see is that the present worths are going to be negative because we're only considering the cost mostly.
Right.
And so for this one, we want to see which one is the least negative, or which one is higher than the other one. And so, it's a little bit of a different mindset, but the same idea, where you're computing present worths, and you want to find which one has the highest present worth, and that's the one you should go for.
Okay, thank you. And one last question. I know that we're doing present worth analysis. Is there like a future sum analysis?
Yeah. So well, there's typically no future sum, because it's the future, you can kind of choose that to be wherever you want.
Oh,
and so usually it's just present sum, but there is one where we convert to a uniform series, and that's called annual cash flow analysis. And so that's what we're going to do next week.
Okay, thank you.
Yeah. Samson, is this the page that you wanted to see? Oh, you're gone. Okay. All right, Sebastian, did you have any other questions? Okay, if not, I'm going to sign off, and I'll see you Thursday, or I guess I'll see you later today for 4:10.